my channel, and today I'm going to be talking about the history of physics. In this video specifically, I'm going to be talking about quantum mechanics. So what is quantum mechanics, or in other words, quantum physics? Quantum mechanics is a field in physics that studies the motion of particles. Now, how does quantum mechanics relate to the history of physics? To truly understand that, we must talk about the history of quantum mechanics itself. German physicist Max Planck was dealing with the ultraviolet catastrophe. This deals with the black body. A black body is a body that absorbs all radiation. Now, when we consider the mathematical model of this problem and compare it to experimental observations, we can see that in some parts the mathematical model is particularly the same as the experimental observations. On another part, it tends toward infinity. Now, this is wrong because it doesn't describe nature accurately, which is bad in physics because physics is trying to accurately represent the universe itself in mathematics. So Max Planck resolved this issue by creating a concept called quanta. Quanta just means a discrete packet of energy, as it's commonly phrased. Now, this infers that we have a particle. Now, later, Albert Einstein, when he wrote his paper on the photoelectric effect, which he later won the Nobel Prize for, also proved that light has to be in the form of a particle. Now, these two scenarios opened up a new era of research and essentially just a new field itself, which is quantum physics. Now, quantum physics, the word quantum, comes from the word quanta, which Max Planck created. Okay, now that we've talked about the basic origins of quantum physics itself, let's talk about how the idea of a particle, for example, a particle of light, essentially helps physics and is beneficial. Now, tons of experimental observations have proved that essentially light is a wave. Now, people like Isaac Newton and Albert Einstein believe that light is a particle. So there's been a lot of debate. Now, here's one of the theories in quantum mechanics: the wave-particle duality. Now, if light can be represented as a wave, light can be represented as a quanta or a discrete packet of energy, which is particularly just a particle, which is it? Now, quantum physics states that in tons of observations, essentially, light is just like a wave. And according to Einstein and the photoelectric effect, light behaves as a particle. So since it behaves as a wave and a particle, light must be a wave and a particle, sometimes called a wavicle. So that's essentially what the wave-particle duality states. The duality is when we just have two things that are particularly the same, in this case, a wave and a particle. So that's what the wave-particle duality states, and this was very important in the field of physics. Now, since essentially Max Planck rewrote particularly the specific theory that involves the ultraviolet catastrophe and resolved it, and Albert Einstein essentially resolved the photoelectric effect and showed that light is particularly just a particle, people essentially just started to say that, okay, now since these two things have been rewritten, we can just create many more things based off of these ideas, like a quanta, which is a discrete packet of energy as it's commonly phrased. Now, people like Niels Bohr and Werner Heisenberg decided to continue on this research, and they even improved it by creating their own ideas, which matches up with experimental observations, which is why it makes quantum mechanics a very beautiful and elegant theory. Okay, now let's talk about the founders of quantum mechanics. Now, if you observed, I wrote founders. Unlike the general theory of relativity and the special theory of relativity, essentially, quantum mechanics just doesn't have one particular founder. Instead, it has many. For example, we have Max Planck, regarded as the father of quantum mechanics. We have Niels Bohr. We have Werner Heisenberg. And we even have Albert Einstein. Now, these people revolutionized quantum physics itself. As we saw, Max Planck and Albert Einstein formed the very basics. Niels Bohr, Werner Heisenberg essentially improved on those ideas, kind of like an innovation is from a pre-existing idea, and essentially just created a new field of physics itself. Notice that Max Planck created quanta for small things, which is a discrete packet of energy as it's commonly phrased, which means that we just have quantum mechanics is dealing with small things. So that's essentially what quantum physics is. it's analogous to just saying that quantum physics is just a theory of small things. That's what we can particularly say. Now, let's talk about interpretations of quantum mechanics. So what are the interpretations of quantum mechanics? Well, Copenhagen interpretation of quantum mechanics is the most popular interpretation of quantum physics. The Copenhagen interpretation of quantum mechanics states that before observing a specific thing, for example, it has a superposition of states. For example, according to Schrodinger's cat, which is a famous thought experiment, if we have a cat, it can be both dead and alive. And there's also a bomb and so on and so forth, but the cat is in a superposed state. It can be dead and alive, but until you observe it, this essentially is just in a superposed state. So the Copenhagen interpretation of quantum mechanics essentially states that we just have a superposition of states. Until we observe it, when we observe, we can find into one state. But on the other hand, before we observe it, it's on both states. It's on a superposition of states. That's what the Copenhagen interpretation of quantum mechanics states. Now, Albert Einstein thought, quote, the Copenhagen interpretation of quantum mechanics is silly. Why can essentially we have an object that can be in two states at once before observing it? This is completely wrong. And Albert Einstein totally disproved the Copenhagen interpretation of quantum mechanics. And there was a long debate between Albert Einstein and Niels Bohr. Niels Bohr and Werner Heisenberg were one of the main founders of the Copenhagen interpretation of quantum mechanics. Albert Einstein often questioned and challenged quantum mechanics, and Niels Bohr mostly came up with an answer. So essentially, quantum mechanics faced a lot of criticism at first, but essentially developed. Now, as you can see, Albert Einstein didn't approve of quantum mechanics itself. One of the reasons is because the Copenhagen interpretation of quantum mechanics is silly, because we can't have superposition of two states in reality, which is particularly hard to complete to our intuition. However, Albert Einstein also didn't like the quantum mechanics as a probabilistic theory. Now, what does a probabilistic theory mean? Well, the probabilistic theory just means that we don't operate on a specific set, so not specific enough to predict accurately. Now, what I really mean by not specific enough to predict accurately just means that this theory of quantum mechanics can't tell exactly where a particle is, or exactly identify where the particle is. We just have a probabilistic approach. We can say that it could be 75% over here, or it could be 25% of the time there. We don't really know. And this is what made Einstein really reject quantum mechanics itself. It's a general theory of relativity. It's a deterministic theory, which means that when we plug in one value or the initial conditions, we can get a specific value, or we can get specific properties, indefinite properties that we know for sure, rather than just a probabilistic approach of quantum mechanics. Nevertheless, quantum mechanics still essentially is an accurate theory that describes our universe itself. And now let's talk about another interpretation of quantum mechanics called the many world interpretation of quantum mechanics. Many worlds interpretation of quantum mechanics. Okay, the many worlds interpretation of quantum mechanics is promoting the idea of parallel universes. So essentially, instead of the superposed state, so if we just write a superposition, of a cat being both dead and alive, and I wrote this more in notation on my video on Bohr cats and symbolism for quantum mechanics, and we have superposition. For example, over here in the Copenhagen interpretation, which we'll call C.I, and on the Hugh Everett, or the many worlds interpretation, which was created by Hugh Everett Third, and when we consider the many worlds interpretation, we state that instead of a superposition of two states, rather one state happens in a parallel universe. So if we just have the superposition of two states, so for example, the cat is dead or alive, in our world, the cat could be alive, but in another world, which is a parallel universe, the cat could be dead. It just happens, a random scenario, that we have an alive cat in this world, whereas in a parallel universe, we have a dead cat. So that's what the many worlds interpretation of quantum mechanics states, and it was developed by Hugh Everett III. So these two, essentially, interpretations of quantum mechanics are the most famous ones. Although the Copenhagen theory of interpretation of quantum mechanics is more widely accepted than the many worlds interpretation, the many worlds interpretation still is a fundamental part of an interpretation of quantum mechanics. Now let's talk about quantum gravity and the conflicts between general relativity and quantum mechanics. So this is a very important part. So we have essentially quantum physics on one side, and we have general relativity on the other. So we have quantum physics and general relativity. Now, how does quantum physics and general relativity have any conflicts? General relativity describes the big, and quantum mechanics or quantum physics describes the small. Naturally, to our intuition, we shouldn't have any conflicting problems over here, but we do. To complete our understanding of the universe, we must have a compatible theory that describes particularly every phenomena in our universe. From black holes all the way to the Big Bang, we must talk about how we can describe everything and complete it into a theory. We must be able to use the same theory to talk about how particles like quantum entanglement moves and and wormholes and all the same things. So with the same theory, we need to describe quantum entanglement, wormholes, Big Bang, and so on and so forth. How can we do that? Well, we already have two existing theories, quantum physics and general relativity. Quantum physics is essentially just a theory that describes the small, and general relativity describes the big particularly. Since general relativity describes the big and quantum physics describes the small, we have two independent theories, which aren't particularly dependent of themselves. Now, when we try to essentially make them compatible to each other, this doesn't work out. Because one, quantum physics is a probabilistic theory, and general relativity cannot be essentially made into quantum physics theory. Now we have two leading theories, string theory and loop quantum gravity. String theory is essentially just creating a new theory. Now, people may think quantum physics describes things at the subatomic level. String theory describes strings at very, 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 very small scales. Loop quantum gravity is intended to essentially quantize general relativity or space-time itself. So loop quantum gravity wants to quantize space-time, whereas string theory is just a new theory on itself. But it makes it compatible. Notice we haven't proved any of these theories yet. If we did, then this would be considered a theory of everything. Another simple approach is to essentially use quantum physics to describe general relativity or vice versa. Now, one possible solution is the graviton. Now, quantum physics is the main subject, and we have particle physics, which is essentially just a branch of quantum physics. Quantum physics describes mainly the motion, whereas particle physics identifies the particular, essentially subatomic particles. So when we have a graviton in particle physics, we want the graviton to be able to describe general relativity or gravity itself. Because when we have a particle for gravity, this makes it compatible. However, we can't prove that we have a graviton because we have tons of infinities in the equations of quantum mechanics. We can't directly prove it because we have tons of infinities. When we're doing quantum mechanics, kind of like the problem which Max Planck had when he tried to resolve the ultraviolet catastrophe, where we had an infinity. We essentially have infinities when we essentially plug in the specific requirements for a graviton. Since we have the specific requirements for a graviton, then we get infinities. So it makes the quantum mechanics equations worthless. Even if they were to work, we'd have to prove the graviton, because the Higgs boson, which is another fundamental particle, even though it was already theorized and the equations were pretty much perfect, essentially it took another n years or something to actually prove its existence of the Higgs boson. So we can prove the existence of the graviton. If we can, this will even make quantum physics and general relativity more compatible, or even compatible itself. So that's the problem. Quantum physics describes the small, but isn't accurate describing the big. General relativity essentially describes the big, but can't describe the small accurately enough. So we need the graviton, or any of these two theories, to essentially replace it. So that's the conflicting problems between general relativity and quantum physics itself. Okay. Now that we've talked about quantum physics, wave-particle duality, the two of the most important interpretations of quantum physics, quantum gravity, let's talk about the mathematics and quantum mechanics. Quantum mechanics involves a lot of mathematics. Like the general theory of relativity, which involves differential geometry, quantum mechanics involves other branches of mathematics. For example, it uses a lot of differential equations and calculus per se. But quantum physics does use a lot of vectors, and general relativity does use tensors per se. So general relativity uses tensor calculus, and quantum mechanics uses a lot of vector calculus. Even though tensors and vectors arise from the same idea, they're different entities, different abstract entities. So essentially, when we consider quantum physics is a pretty mathematical concept. Unlike other theories, except for general relativity, quantum mechanics tries to understand the universe in a way using mathematics. So quantum physics and general relativity truly prove that the language of our universe is mathematics. Now that we've talked about that, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.